Hey everyone, thank you for joining this talk about network movement abilities and best practices for implementing them. My name is Shikang. I work at Epic Games in the technical developer relations team, and I specialize in gameplay systems like the character movement components and gas. Now we are here because every game wants fun movement, but it turns out that network movement is quite a difficult topic. And this is multiple reasons. It all starts with this pesky requirement that we want our movement to feel responsive. So the moment I tilt my joystick, the moment I press a button to activate an ability, we want to see an effect right away. So the game client will predict some of that outcome. But we also want our character to appear to have the same position on my client, on the server, and on other clients. And if that's not the case, then we want to correct that in a way that hopefully doesn't feel too jarring. We want our gameplay to feel fair for all players, and we also want our networking code to be difficult to exploit. Now, these are quite difficult requirements to strive for all at once. The goal for today is to have everyone here understand the character movement components networking model, to foresee the challenges that you will encounter when working with this model with another replicated system, for example, the gameplay ability system, to know your options for addressing those challenges. And I'm also going to share some ways to debug your movements, and all of this will hopefully help you plan your new movements, verbs, and abilities. This talk is going to be relevant for any networked Unreal game that uses the character movement components. Now, Unreal also provides this new movement solution called the Mover plugin. As of right now, UE 5.6, that's still in beta, so we're going to focus on the mature solution that most people here will be using. If you're interested in the Mover plugin, there's a great talk from Unreal Fest last year called An Introduction to the Mover plugin. Now, even though I will be demonstrating CMC and gas today, the knowledge here is really relevant for any ability system or any gameplay code that uses RPCs. We're going to cover things in this order. First, I'm going to talk about networking conditions, then provide some tips for how to debug your movements. Then I'm going to give some information about CMC's networking model, and then best practices for interacting with that model to create your movement abilities. But first, let's start with networking conditions, because these are basically the antagonists of this whole story. When you send data over the internet, you're sending packets, and those packets will have a delay, so latency. That latency will be unpredictable and variable, which we call network jitter. That can cause your packets to arrive out of order as well. Packets can also be lost on the network, so they might never arrive. Unreal provides multiple ways to communicate between the client and server, and each come with their own characteristics. What Unreal provides is reliable RPCs, unreliable RPCs, and property replication. Now, RPC, remote procedure call, refers to calling a function on one end, for example, the client, but that function executing on the server. The nice thing about reliable RPCs is that when you call them, Unreal guarantees that they will execute on the other end, as long as the object is still alive. And another nice thing is that if you call multiple reliable RPCs on the same actor or on components belonging to that same actor, then all of those RPCs within that actor scope will also execute in the same order. This is implemented by resending if needed, and also to guarantee that they execute in the right order. An RPC might need to wait before a previous RPC arrives. You have to be careful with this, though, because if you send RPCs too frequently, then the client may need to, one end might need to resend, might need to hold on to more RPCs to resend. And that buffer can grow and grow and grow. And if it hits a limit, then the client will get disconnected. So the guarantees are nice. They come with some drawbacks, and you have to make sure you're not sending too often. On the other hand, unreliable RPCs don't have any of those risks, but also none of those guarantees. Now, property replication is another way to communicate, only from server to client, but we'll be focusing on RPCs. Something that's not guaranteed, even for reliable RPCs, is that when you send 2 or more RPCs in the same frame, then they won't necessarily arrive or execute in the same frame on the other end. So if you have multiple replicating systems like CMC and gas, then even if something executes on client in the same frame, it doesn't necessarily execute on the server in the same frame. That will affect the outcome, and that can cause corrections. I made a very simple movement ability to demonstrate this. So this movement ability just teleports my character 2 meters forward, and it's a local predicted ability in gas. So what will happen is when I press a button, my client will first execute this, so move me forward. And it will also send a RPC to the server, so gas's try activate ability, to the server, so the server will also execute the same logic. Now, if things arrive at the same time, things go really well. But if it doesn't, for example, my ability RPC arrives late, then the server receives a move with my new position, but doesn't see a reason for me to be that far. So the server will send a correction, and the client will take the correction and teleport the player back, or correct the player back. Now, then later on, when the server does receive the RPC, it will be like, hey, what are you doing back there? And send another correction. So you get corrected back and forth. In practice, that looks like this. The first few times it goes well, but when it goes wrong, it goes really wrong. Like here, ouch, ouch. Yeah. So even with a simple ability, things can go very wrong due to this network jitter. In general, I call this the RPC arrival timing issue, so network jitter and packet loss. To generalize this problem statement, when you're working on movement abilities, what your main challenge is that the client and the server's state for the character and the world will always differ slightly. The RPC arrival timing issue is one reason for this, but also the fact that the server and client are fundamentally always a little bit distinct is another reason. What I mean by this is the client is always a little bit ahead of the server because it's predicting for your character's location. But the server will be ahead of your client for server-controlled actors like NPCs and projectiles. Meanwhile, other clients are ahead of the server for their position, and they are 2 steps ahead of your client for their character position. To add more complexity, your client, the server, and other clients will also tick at different delta times. Even if they're configured with the same frame rate, hitches can cause different delta times. Now, all of these noise factors cause divergence between the server and clients. That makes it difficult to keep all of these world states in sync, but also difficult for the server to validate whether your sent move is correct. And even more so when you need to validate a predicted move based on a predicted ability or a predicted ability based on a predicted move. And when you're not aware of all of these like noise factors, that leads to unnecessary movement corrections and ability rejections. Unless you know what you're doing, you see all of this coming, and you take this into account and have your own solutions for this. Now, before I move on to more theory, I want to give some ways to debug your movement. The first one is basic. You can enable network emulation in Pi to emulate latency and packet loss. You can find this under your advanced settings in your Play drop-down menu or in your editor preferences. Now, this is useful for many purposes. If you configure fixed latency, you have a way to trigger a correction in a very, very controlled manner. For example, if I configure my latency to be 150 milliseconds, and something happens on the server that my client didn't predict, I know that in 150 milliseconds, my client will receive that correction. You can use this to test your correction and resimulation logic. Now, what I mean by resimulation is that when you send a move, let's say I'm walking. So when you send a move, by the time that move arrives on the server and the response arrives on the client, time will have passed. So if I take the server's correction, I will be like moved back in time. But I don't want that. So what the client will do is it will keep a recent history of moves and then repredict any move that happened since that older timestamp. So it doesn't feel like the player got teleported back in time. Now you also have, so when you configure variable latency, so difference between minimum and maximum, then you will also reproduce the RPC arrival timing issue. You'll get RPCs arriving out of order. And you have to test for this because this is going to happen in the wild. If you have packet loss, then some of your inputs in moves might also be dropped because those moves don't arrive. And you also have to test for this. Even with reliable RPCs, packet loss can cause those RPCs to be resent. So that's additional latency, another round trip. We recommend to test at least with average network emulation, so a little bit of variable latency and packet loss, because that will trigger each of these problems. Now here's another nice console variable. If you turn on p.net show corrections, it will draw on the client some debug info when a correction takes place. It draws a red capsule for where your client predicted the character to be, and a green capsule for where the client placed it after taking the server correction and after resimulating moves. So it's a complete like before and after info. This looks like this. And you see here that when a correction happens, it happens in the stream. Here I have a volume that's only on the server will push my character sideways. And the reason why corrections happen in the stream is because in the time it takes for you to receive a response from the server, you all have already sent multiple bad moves. Now, net corrections or show net corrections is great because you see the before and after. But often when you make new movement verbs, you also want to check what happens like in those in-between steps, because all that correction and resimulation all happens in one tick. What you can do then is add events to your visual logger and to play back those events and inspect them in the timeline. That can look like this. So I trigger the correction again, pause the game, I click my event, and then I can see the complete breakdown of the correction and the result of every resimulated move. Some good functions to override for this are CMC's on-client correction receive, which gets the server corrected location, and saved moves post-update function, which gets the result of each resimulated move. Now here's a trick that's quite quirky, but useful when testing locally on a machine, and when you're running the server and the client under a single process. You can make use of the fact then that the server and client share the same memory and variable namespace to instantly communicate between the server and client for testing purposes, even with network emulation enabled. I'm using this here to visualize the server's character position on my client so that I can see the effect of latency, so how far the server is behind, but also if they are accumulating error over time. A useful tip here is if you are testing with the server and multiple clients, all still locally and under a single process, then you might want to have like the same index for a player between the server and client. One way you can do this is by grabbing the game state's player array, making a copy of that, sorting that, and then find one player state in that array. Then the server and client will agree on the index per character. You have to sort the player array because the game state's player array is sorted differently per client, because we decided at one point to always have your player state at index 0. Now let's dive into the character movement components networking model. So what are we dealing with, and because we need to work together with it. I'm going to focus primarily on autonomous proxies, which means the character that I'm controlling, and the networking that happens between my client and the server about that character. The reason I'm focusing on autonomous proxies is because sim proxies, so other clients, their representation of my character, are quite simple by default. Other clients will just take the last server position and smooth towards that position. And in some cases, if the difference is too large, they will just teleport a little bit. So the complexity is in the autonomous proxy and the server. Let's start with how my client sends moves for my character. So the client sends moves to the server many times per second, and the server will send a response for each of those moves. If you look into the character movement components code, you'll encounter two important move classes. There's a saved move and there's network move. This is network move. In the saved move, the client records everything that's needed in order to resimulate recent moves if needed. The network move contains everything that the server needs in order to execute the same movement. Now, both the save move and the network move contain a client timestamp, which the server will use to update the character movement with the same delta times, and also some inputs like my control rotation, whether I want to jump and crouch, and the acceleration that the client applied. The client will also send some outcome, but this is mostly used on the server to compare. I want to note here that the client timestamp that we send is not like the client's world time, but rather it's a CMC-specific timestamp that gets rolled over back to 0. And this is mainly so we can save some bits when networking. So don't assume that this is a constantly increasing time. It also has no meaning on other clients. I'm going to dig into two more important aspects of move sending, move combining and important moves. So every time the server receives a move, it's more stuff to process. And moves are quite expensive because you're doing line traces, you'd have to do collision checks. So if a client is running at 120 FPS and the server has like many of these clients, many players connected, that's a lot of server workloads. So to manage that a little bit, what we do is we let the client combine similar moves before sending it to the server, as long as that movement is similar over multiple ticks. So for example, if I'm moving in a straight line, or if I'm strafing one direction, or if I'm just falling through the air, these types of moves the client will combine over multiple ticks before sending to the server. The logic for whether moves can be combined can be found in save moves can combine with. And as you are working on your new movement verbs, you often have to revisit this function and override it. The maximum time that the client will combine moves with is configurable as well. You can either override CMC's client net send delta time, or configure client net send move delta time in your default game.ini. In a fresh Unreal project, this is configured so that you send about 60 moves per second. So you combine moves up to a 60th of a second. Now, move combining introduces a delay, and a delay can work against you. It's a very common cause of movement and desync problems. So when you are working on movement and you see that like you suspect that maybe move combining is the cause, then you can turn off move combining by setting p.net enable move combining to 0 to rule it out. Use this for testing purposes only, because if you send move every tick, that can get quite expensive on the server and also cause a lot of network traffic. Another tip is that at any point in time, you can call CMC flush server moves on the client, and that will send any combined move that it has combined over the last few frames. Now, gas does this already when you activate a local predictability, so it's not a low-hanging fruit there. But if you use a different ability system, or if you send your own gameplay RPCs, which really want the server to have the latest character position, then you can call flush server moves. But you still have to take into account that even if you flush server moves, it's still not guaranteed that it will arrive in the same frame on server side as other RPCs you call that frame. Now, tweaking move combining is quite a nuanced problem, because if you send moves too often, that causes server CPU load. And it's very useful to be aware that if you are playing root motion montages, or if you have a root motion source active on the character, you'll send moves every frame. So that's something to be aware of. I'm going to go into those root motion sources and montages in a little bit. On the other hand, if you're combining moves over too long of a period on the client, you might think that's really efficient. But that also causes a different problem, client-side CPU load. Because what the client does when it sends a combined move is it will also first restore the character's pre-combined position and then replay that same move client-side. And this is meant to maximize the outcome of the client and server having the same result. But if you use a large delta time, there are movement modes in the CMC that will trigger substepping. It will consume some of the delta time, but trigger another iteration. Now, another important aspect of move sending is important moves. Because your move RPCs suffer from packet loss, their CMC has a mechanism to work with this. CMC can mark some moves as important. This logic is in save moves is important move. And what it then does is, if a move is important, it will be sent redundantly. So when you send a new move, then the oldest important move in your recent move buffer will be resent again. This greatly increases the odds of that move arriving. But it's still not perfect, because packet loss can still cause everything not to arrive. And if you have multiple important moves in your move buffer, then only the oldest one gets resent, so they can overshadow each other. Just like move combining, if you add new movement verbs, it's often a reason to revisit your important move logic. Here is an overview of what you're sending when you send the move. When you send the move, it's triggered because either the get client net send delta time has passed, or because the new move was uncombinable. You might also send a combined move that you've been building up over the past few frames, if that combined move was not combinable into the new move. And if there's also an important move in your recent buffer, then that gets sent as well. So when you send a move, it's often 1 up to 3 moves. Now, what does the server do when it receives a move? The server will process every move immediately. So what it will do is it'll take the client-provided timestamp and compute the difference between them and use that delta time to advance movement server side. And this is so that network jitter doesn't cause the server to use like a different timing than the client. But the server will skip over moves that haven't arrived yet. We really prioritize sending a response as soon as possible and also executing moves as soon as possible. That means the server can skip over a move and apply a larger delta time. And that's another reason for divergence. What the server will do is take the client sent inputs, so from your network move data, apply them to the character and then call perform movement. The client also originally called perform movement to get its movement outcome. The server doesn't roll back the rest of the world, so that's something to be aware of. That's mostly a cost-saving reason. And if the outcome of the server and the client is too different, then you get a correction. By default, a reason for a correction is either a difference in location outcome or a difference in movement mode. The movement mode refers to that enum where a character is either walking or falling or swimming and so on. And in terms of positional error, it's configurable in your INI file as max position error squared. By default, it has a value of 3 squared. So the squared value of 3, which means like 1.7 centimeters of error tolerance. Now, the logic for this you can find in server check client error and server exceeds allowable position error, which are great functions to study, but also to override. And we'll give some examples later on. Now, here I made a video to demonstrate when a correction triggers. I'm pressing a button here to intentionally introduce some error client-side. And I greatly increase the positional error tolerance to demonstrate that the client and server will be applying acceleration independently until a correction happens. And when the server starts falling, when the client doesn't, that causes a correction. Or here, when the client starts falling, when the server doesn't, that also triggers a correction. Now let's talk about what the client does when it receives a correction. The response that the server sends and all the data in it is in character move response data. What that contains is a timestamp, which is the original client sent timestamp, so that the client knows which move in its move buffer it's a response for. It contains whether the server found the move OK or not. And if not, then the server also sends along correction information. That includes your location, the server-side decided location, velocity, movement mode, movement base, and also a complete server snapshot of root motion sources if there were root motion sources active on the server. I'll get to that in a bit. By default, the server does not correct rotation, but if you wanted to, then you can override CMC's should correct rotation function to return true on the server. Now, as you work on new movement abilities and movement types, typically you want to create a subclass of character move response data so that you add more ways for the server to correct the client. For example, to correct them onto a zip line. Then, after the client adopts the server-side outcome, what it will do is it will resimulate moves so that it doesn't feel like the client gets moved back in time. Adopting the server outcome happens in client adjust position, and then the next tick in client update position after server update, every saves move with a more recent timestamp will be resimulated. What will happen is that each save move will restore some variables onto the character or onto the character movement component, and then perform movement is called again. So perform movement is a really important function because it gets called when the client originally predicted movement. It gets called on server when the server executes the client received move, the client sent move. And on a correction, the client will call perform movement again to resimulate. I want to dig into one more feature of CMC before we move on to best practices, root motion sources. So root motion sources are really the way for, our CMC feature to provide additional velocity modifiers over time. They are implemented as subclasses of F root motion source, and GAS provides ability tasks to manage your root motion sources. The nice thing about root motion sources is that they are evaluated at the right time, so inside your perform movement function. So whether you are predicting or the server is executing your move or when you're resimulating, those root motion sources are evaluated in each of those scenarios and with the correct delta time and time since the start of that source. So in the case of prediction, it's the client's world time. On the server, it's the delta time from client received moves. And on resimulation, it's the client's old world delta time. Now, root motion sources are not sent from the controlling client to the server. Instead, when you want to use this, the client and the server must apply the same root motion source. Out of the box, the only way to achieve this is by using gas, because if you have a local predictability in gas, they both execute the same blueprint, so they will apply the same root motion source, hopefully, with the same parameters. I do have to mention here that if you use root motion sources and use gas to trigger this, you still suffer from the RPC arrival timing issue. Root motion sources can be replicated down from the server to clients. For the autonomous proxy, so for the controlling client, that's the case when the server sends a correction. And for SIM proxies, that's always the case. The server sends down root motion sources to SIM proxies. The initialization of those SIM proxy root motion sources happens through a replicated ability task from GAS. And any updates, like any state changes, get replicated down from server to client through the characters rep root motion property. Now, root motion montages, I'm going to skip over this, but I'm going to skim over this, but they have the same advantages and the same drawbacks. I want to reiterate that root motion sources prevent move combining. Be aware of that. So they can they can trigger costly networking and server-side CPU load. Now let's dig into some best practices. So the first thing you want to do is to focus on maximizing your accuracy. So a general piece of advice I have is you don't want to fight the character movement component, because consider this. When the client receives a correction from the server, it will teleport the character location to the server-side outcome and then resimulate safe move. So if you have any effect client-side that isn't re-evaluated in those steps, then that effect will be stomped. Instead, what you want to do is to handle all of your movement inside perform movement, because it is called in each of those contexts and also is called on resimulation. What you want to avoid is modifying your character location and velocity in tick functions. Now, what people tend to do is put their movement logic in character tick or in their CMC tick function. This is bad. And the reason for this is because tick is not called on resimulation. You also want to avoid modifying velocity and location in other actors tick functions. You don't want to modify your character's location either from other actors. And let me give you an example. If I have a wind volume that will nudge my character in the wind direction on every tick, well, the time between the client sending two moves might be different than the time between the server executing those moves. So then the server may have ticked a little more or less, and that just causes additional divergence. What you always can do in these cases is to handle things in perform movement. So in the case of this wind volume example, you would have perform movement, poll the wind volume's parameters, and then evaluate with the correct delta time. Now, for handling things inside perform movements, there are a couple of options. You can override your CMC's phys functions. So start new physics, which is called in all situations, and phys walking, phys falling, phys custom, phys swimming, and so on, based on your current movement mode. If you need to send additional information from the client to the server so that the server can execute the same move, then you also have a couple of options. You can either extend your CMC's network move data class, or you can introduce custom RPCs to update the server-side inputs. You can also use root motion sources. The nice thing there is that Unreal provides some common ones already. Another nice thing is that because applying the root motion source server side cannot be done by the client, only indirectly by triggering the same ability, it's a bit harder for the client to lie about data and parameters. But again, the main issue there is that you are sending another RPC, so you are suffering from this RPC arrival timing issue. Now, when would you use which? It really comes down to this. You can extend, the nice thing about extending network move data is that this way you can avoid that RPC arrival timing issue, and that maximizes consistency between client and server. But it is also a lot more engineering work, because whenever you add parameters to network move data, you have to make sure that players or cheaters can't exploit this by lying about those values, by manipulating memory. You also have to make sure that your network move data class doesn't get too bloated, and you have to serialize it over the network in an efficient way. For example, if you have like 10 parameters for ziplining, you don't want to send all of those 10 parameters when you're not ziplining. The nice thing about root motion sources is that it's less engineering work because there are some default types already. And they also only have a net serialization cost when they're active. So it's a bit easier to keep that efficient networking-wise. But again, that suffers from the RPC arrival timing issue, and also having root motion sources active prevents move combining, which can be costly. Now, I want to share here that Fortnite heavily leans into the approach of routing everything through network move data, where we have a system where you can create classes that extend the movement mode, and each of those classes can feed their own data into save moves and into network moves. In Fortnite, we're also slowly moving away from using root motion sources to reduce server-side CPU load. But the best choice for your project really depends on a lot of factors. For example, how much engineering power you have available. The next best practice is you really want your server to do the same thing as the client as long as there's no interruptive factors. So you either need to send everything from the client to the server needed for that, but in some cases you don't have to if the server and client can both derive some movement effects in the same way. For example, if you have a stationary volume like currents, waterfalls, or if both the server and client can evaluate like the same effect from the current time. Now, if you want to do things time-based, you should consider sending the clients what the client thinks that the server world time is with the move. Because by the time that the client's move arrives on the server, the server-side timestamp has already advanced a bit. What you want to be careful with is having both the server and client be smart. And a prime example for this is if you are working with moving replicated targets. So this concerns motion warping as well as root motion sources, which both provide ways to, for example, home towards a moving target. Now, the reason this is quite risky is because if an NPC is server controlled, the client will already be a little bit behind for that NPC's location. And by the time the client's move arrives on the server, that NPC will have moved even a bit further. So the client is actually 2 steps behind, or 2 steps behind by the time that move arrives. So I created an example ability to demonstrate this. Here I'm using motion warping to warp towards a moving actor that is server controlled. And the server will also, upon receiving this ability RPC activation, will also start motion warping, but then with the server-side location of that actor. And that can look like this. So you get huge corrections because there's basically a round-trip latency of difference between the actor position. Now, what you can consider instead is to let the client decide a point to motion warp to, and then send the same point to the server, and then have both motion warp towards that point. Then at least the client and server will both have the same trajectory, but you still might suffer from RPC arrival timing issues because we have introduced another RPC here. So this is how that looks when the client decides a point and the server also motion warps to that point. Much better. Now, the next best practice is to record your resimulation dependencies or your movement dependencies into save moves. Because when the client receives a correction and resimulates moves, some time has already passed in the world. So other actors may have moved farther ahead in time. Your attributes may have changed, like your gas gameplay attributes. So when you resimulate the move, it might not be totally accurate. What you want to do is to record everything that CMC needs to resimulate that move accurately. When you are calling perform movement, or when perform movement is executed, you can check the character's client updating boolean and check whether it's true. If it's true, that means you're currently replaying. And then you can get the currently replayed save move by calling get current replayed save move to get the recorded data from that save move. Let's talk about security. Now, whenever you add parameters to a network move data, or whenever you introduce an RPC, you have to validate those parameters and whether that RPC is called in the right context. Because cheaters will try to exploit this. They will try to lie about that network move data or call those RPCs with wrong values. So in the previous example where I let the client send a point to the server, you can imagine cheaters will try to exploit that by just sending a point that's halfway across the map. And if the server just motion warps to it, so interpolates towards that, you can use that very easily to cheat. So always always validate, either by accepting or rejecting that request, or by clamping the value. So that, for example, you only motion warp towards a point that's close enough to the player. This is also fun when you want to mitigate lag switch exploits. Now, we learned that just now that the server only advances the character movement when it receives that move RPC from the client. You can imagine that's quite exploitable if a cheater decides not to send any moves. Now here's a fun fact. By default, CMC won't even take gravity server-side if it's not receiving moves. It will look like you are falling on other clients, because those other clients will extrapolate your movement, because there we prioritize like movement looking smooth. But on the server, the character will stay in the air if the client stops sending moves in the air. So here, when I'm jumping off the stairs, I'm not sending moves, and you see my server-side location remains in the air. And only when I send moves again, then it gets updated. And the reason I'm starting falling again from the air is because the server will only apply like a maximum delta time. Now, what can you do to mitigate this? There are two useful functions for you to override. There's force position updates, which get called one time when the server hasn't received moves for a while. And there's tick autonomous proxy, which the server will always call. Now, Fortnite uses a combination of force position updates to raise a flag, and then in tick autonomous proxy, we'll tick gravity on the server. This is so that players can't stay in the air forever. So you should also consider how players can exploit using lag switches in your game, and then use these functions to mitigate that. There are cases where you might want to decide not to predict. So you don't want to predict something if it has a chance of a huge correction. In those cases, you can consider just letting things happen on the server. You also generally don't want to predict movement effects on other players, because your client is already 2 steps behind for that other player's location. And that player can also interrupt whatever you want to do with them. Now here's an example from Fortnite. In Fortnite, you have a knockback grenade, which can knock back other players. But the other player can also put down a wall to prevent that from happening. So if my client will knock that player back, but the other player put down a wall in time, and that request arrived on the server in time, then it just means that on my client, their character is being teleported back and forth, which is not a nice experience. So in those cases, you can consider just letting the server do it, and to mask the latency, perhaps with a wind-up animation or with audio visuals. Now, after you've applied those best practices to maximize your accuracy, maximize the odds of your client and server having the same outcome, then what you can do is to add some leniency to the correction. To correction triggering. Because even after you apply those best practices, some sources of divergence will remain. If you're using multiple RPCs, then you still have the RPC arrival timing issue. And even if you have only one RPC, CMC moves can be skipped due to moves arriving out of order on the server. So the server applies a large delta time. Inputs might be dropped due to packet loss. The server and client are always still desynced. And there are factors that the client couldn't predict. Some things, like sometimes it's even due to cost saving that for example, we intentionally not roll back the world on the server because that would just be too costly for many players. What you can do then is to be a bit more lenient on correction in some situations. Now remember that there is this tweakable max position error squared, but Since that's fixed, it's often a bit too rigid. What you can do is to override your CMC's server exceeds allowable position error to apply a different positional error tolerance. This is mainly useful if, for your movement ability, the trajectory is somewhat the same between client and server, but mostly the timing might be a bit different. So for example, if your move has the same endpoint because you're grappling towards a wall, or if it has the same trajectory because you're playing a root motion montage, or if perhaps due to physics, you expect it to end up in the same location because things will be corrected when you're falling and you hit the ground. Then you can use a temporary contextual, temporary different error tolerance. If you don't expect to end up in the same location, you can still use this, but try to mask that fact by manually correcting the client to the server side position. There might be cases where you want to skip corrections. For example, if you're attaching the character to a vehicle, we are already doing our best to keep the vehicle location synchronized, so we don't have to do character correction checks. Then for the server side, you can override server check client error to early return to not consider corrections. You can also decide to skip corrections client side, which is useful in situations like if you're playing a synced animation and you prefer that synced animation playing out smoothly, even like accepting some error. Now let's get into some risky practices, but still useful. Sometimes you might want to prioritize the player's feel. And in those cases, you can let the server adopt the client-side outcome. This is quite risky, so use it sparingly. So if you set CMC's server accept client authoritative position to true, then the server will accept the client-side outcome as long as it's within that error tolerance, either that fixed one or that dynamic one that you decided. This is useful for volatile movement, like if you're performing very sporadic movement, or if you're playing a root motion montage and you expect that RPC arrival timing issue, then you can add some leniency and let the server accept the client's position so that errors don't accumulate over time. Try to avoid using this too much. So first try those other solutions. And when you do let the server accept client outcome, only do this for short time frames. The drawback is that cheaters can try to lie. With each move, they can try to exploit that little error tolerance to move just a little bit faster. Now, here's a very bad practice. I'm just calling this out because this is very popular. This is something most devs will try early on when they're experimenting with CMC. You can also let the server always adopt the client-side position because it feels great for the controlling client by setting server accept client authoritative positions to true and ignore client movement error checks. Now, when you do this, you really will get cheaters that will teleport all over. In my personal experience, I once worked on ship title where we accidentally left this on. People only took 2 hours to find out, and that was in a small indie game. So it's going to happen in minutes if you're working on a popular game. It still might be useful if you're working on a PvE game and you don't care about cheating. Now, that's all I had. It was a lot of information, so I hope you found this useful. We covered how to debug your movements. We covered CMC's networking model. We covered all the problems that you'll face, like RPC arrival timing issue, fundamental desync between server and client, different delta times, and how to best handle these. So first, prioritize increasing your accuracy. Handle everything through perform movement. Replicate everything that's needed for the server to do the same move. Make a weighted choice between network move data or solutions that use more RPCs, like root motion sources or custom RPCs, based on whether you have engineering power available. And also maximize the accuracy for your resimulation. And after doing all of that, you can consider adding a bit more leniency by having this dynamic error tolerance, or by letting the server accept the client outcome a little bit. So I hope you found this useful. Thank you very much.